All right, first reaction of amide is acid catalyzed hydrolysis. You have seen hydrolysis for many times now. All right, this another one. Everything can do hydrolysis basically, but the yield is not good or bad. It depends. All right, so amide can be cut by water. So, but it needs to be catalyzed by the acid because if you look right here, start with the non-reactive starting material and less reactive, not that reactive nucleophile like water. You guys know, so we have to activate it. All right. Now, since we add an acid, now take a look. So at the end, the amine comes off and become an ammonium ion. Okay, and the reason is, well, when you add an acid, so we have hydronium ion floating around, pKa negative 1.7, ammonium ion pKa 9.2, totally go to the right, favor the product. Okay, the mechanism goes like this. All right, first step, adding an acid, protonation. Of course, the localized electron take the proton first. All right, then water can attack. Okay, almost get to tetrahedral intermediate, but you have to get rid of the charge, right? So deprotonation, here we go. That's a tetrahedral intermediate. All right, let's say what else we have to do. So we're halfway now, similar to alcohol, really similar to that, like esterification. What else? So we need to get rid of NH2 group, so it will come out as ammonia. So we're gonna protonate it. Ta-da! All right, so we're ammonium ion now, so a better leaving group, and then we're gonna use any lone pair of oxygen. Pick one. All right, there are 4 total. Pick one. Kick out the ammonium ion. All right, and you get this compound, and then amine that comes out. You can use amine. You can use water, and then grab the proton, deprotonation, and you get ta-da right here. Fix for me real quick. So NH4 plus, not NH3 plus. All right, NH4 plus right here. All right. So this is acid catalyzed hydrolysis. So this can happen under basic condition as well. Let's take a look. All right. This the mechanism just like saponification, like making salt. Take a look. Start with acetamide, add an hydroxide ion, attack nucleophilic attack on carbonyl carbon, and then loss of leaving group. So amines is gonna leave as an amide, NH2 coming out. Okay. Now I'll be like, hey, hold on, NH2 minus amide leaves as a leaving group. But yeah, just like the saponification, right? Or you have seen like a methoxy group leaves before, right? And the reason is, well, we start with a reactive compound. So you're starting out with a species that have charge already, so a reactive compound. Activation energy is not that high. If you start out with a neutral compounds, yeah, this is probably not going to happen. Big activation energy. All right, that's one reason. There's another reason why amide leaves. Next step right here. So we have amide deprotonation, make a carboxylate. Making salt, that's one of the best driving force you can have. Making salt really stable. Think about salt like sodium chloride, highly stable. Charge interaction, this ionic bond, really stable. And the last step, the second step here, not the last step here, so it's irreversible. Okay, because of salt formation. All right, so there are 2 factors why amide leaves. All right, so I think so. That's pretty much it. Oh, we have one more. So that's the reason why the second step is required. You have to do acidic workup. Otherwise, you're not going to get the acid back because you have to protonate it. Okay. All right, that's hydrolysis. So let's moving on to reduction of amides on the next one.